August 17, 1943. Schweinfurt, Germany. Second Lieutenant Robert Rosenthal gripped the controls of his B-17 Flying Fortress as flak exploded around him. The mission to destroy ball-bearing factories deep in Germany had turned into a nightmare. Of the 230 bombers that departed England that morning, 36 would never return. But what Rosenthal witnessed next would haunt him for decades. A B-17 from the 381st Bomb Group took a direct flak hit to its right wing. The explosion severed the wing just outboard of the No. 3 engine. The massive bomber, suddenly asymmetric and unbalanced, rolled violently to the right. 9 men were aboard. 9 men whose survival now depended on whether their pilot could do something that training had never prepared them for: control an aircraft that aerodynamics said should be uncontrollable. Rosenthal watched as the crippled bomber began a slow spiral toward Earth. The pilot was fighting, that much was clear. The aircraft would stabilize briefly before rolling right again. Each recovery took longer. Each roll became steeper. At 18,000 feet, white parachutes began to blossom. The crew was bailing out. At 12,000 feet, 3 more chutes. At 8,000 feet, the bomber entered a terminal spin. 2 men remained aboard, likely the pilot and co-pilot, fighting to the end. The B-17 impacted a forest north of Schweinfurt at over 300 miles per hour. There were no survivors. What Rosenthal could not know was that hundreds of other pilots would face this same impossible situation in the months ahead. And some of them would discover that the impossible was merely improbable. The strategic bombing campaign against Nazi Germany represented the most ambitious aerial operation in history. Beginning in earnest in 1942, the United States Army Air Forces committed to a doctrine of precision daylight bombing. The theory was elegant. Heavily armed bomber formations, flying in tight defensive boxes, would penetrate German airspace in daylight, strike strategic targets with precision, and fight their way home. The Boeing B-17 Flying Fortress became the primary instrument of this strategy. Designed in the mid-1930s, the B-17 incorporated revolutionary features for its time. 4 Wright R-1820 Cyclone engines, each producing 1,200 horsepower, gave it the range to strike deep into occupied Europe. Defensive armament eventually grew to 13.50 caliber machine guns. The aircraft could carry up to 8,000 pounds of bombs, though typical combat loads were closer to 4,000 pounds to extend range. The B-17's wingspan measured 103 feet, 9 inches. This dimension would become critically important in ways designers never anticipated. The wing was built around a massive main spar, a structural beam running the length of each wing panel. This spar, constructed from aluminum alloy and measuring over 50 feet from root to tip on each side, provided the structural strength to carry the aircraft's weight and resist the bending loads imposed by flight. Consolidated's B-24 Liberator complemented the B-17 in European operations. The B-24 featured a high-mounted Davis wing with a span of 110 feet, designed for efficiency at high altitude. The wing was thinner and more aerodynamically refined than the B-17's, generating less drag and allowing higher cruise speeds and longer range. This efficiency came with trade-offs that would become apparent under combat damage. Both aircraft types flew in massive formations. A typical combat box might contain 54 bombers arranged in precise 3-dimensional geometry. Lead bombardiers would sight on the target while dozens of other aircraft dropped on their signal. This formation bombing sacrificed the precision that doctrine promised, but provided mutual, defensive fire against attacking fighters. The formations also created aerodynamic challenges. Aircraft flew within 50 feet of each other, wingtips nearly overlapping. Prop wash from preceding aircraft created turbulence that required constant attention from pilots flying in trail positions. Engine exhaust, hydraulic leaks, and battle damage added visual markers that pilots used to maintain station. German defenses evolved rapidly. Flak, anti-aircraft artillery fire, created deadly boxes of airspace through which bombers had to fly. An 88mm flak shell contained approximately 20 pounds of high explosive surrounded by a pre-fragmented steel casing. When the time-delayed fuse detonated the shell, typically at altitudes between 18,000 and 26,000 feet, it created a sphere of metal fragments moving at supersonic velocities. The fragments ranged from fist-sized chunks of casing to tiny slivers of steel. The larger fragments could penetrate aluminum skin, sever control cables, rupture fuel tanks, or destroy engines. The smaller fragments peppered aircraft surfaces, creating drag and weakening structures. A single flak burst could damage multiple bombers if the formation was tight enough. Messerschmitt Bf-109 and Focke-Wulf Fw-190 fighters represented the second threat. German fighter tactics evolved throughout the war, but the fundamentals remained consistent. Attack from angles where bomber defensive fire was weakest. Press attacks home to point-blank range, and concentrate fire on specific aircraft rather than spraying the formation. Head-on attacks proved particularly effective. A fighter approaching at a closing speed of over 500 miles per hour provided bomber gunners only seconds to engage. The fighter pilot aimed for the cockpit and engines, areas where a few hits could cripple a bomber. As fighters flashed past, they might fire another burst into the wing roots or bomb bay, seeking to ignite fuel or detonate ordnance. Combat boxes flew at altitudes between 22,000 and 28,000 feet, where temperatures routinely dropped to -40 degrees Fahrenheit. Crews wore electrically heated suits that frequently malfunctioned. Frostbite was common, as was anoxia when oxygen systems were damaged. The physical environment was hostile, even before enemy action. Missions could last 8 to 10 hours from takeoff to landing. Pilots spent this time maintaining formation position, a task requiring constant attention. The B-17's controls were not hydraulically assisted. Every input required physical force against aerodynamic loads. After hours of formation flying, pilots' arms ached and hands cramped. The strategic effectiveness of the bomber offensive remains debated by historians. What is beyond debate is the cost. The 8th Air Force, operating from England, would suffer over 47,000 casualties, including more than 26,000 dead. The loss rate approached 5% per mission during the campaign's worst periods. A crew had to survive 25 missions to complete their tour. The mathematics were grim. The first documented case of a B-17 losing a substantial portion of its wing and surviving occurred on October 8, 1943, during a mission to Bremen. Lieutenant William Lawley's aircraft, Cabin in the Sky, took a 20mm cannon hit from a Focke-Wulf 190 that detonated inside the right wing approximately 8 feet from the wingtip. The explosion destroyed the wing structure outboard of the impact point. Approximately 10 feet of wingtip, including the aileron and trim tab, simply ceased to exist. The remaining stump showed exposed spars and stringers, with aluminum skin flapping in the 200 miles per hour airstream. Cabin in the Sky immediately rolled right. Lawley instinctively countered with left aileron and left rudder. The aircraft stabilized, but at a 15-degree right bank angle. Every time Lawley tried to level the wings, the asymmetric lift pulled them back to the right. He discovered that by maintaining significant left aileron input and substantial left rudder trim, he could prevent the roll from worsening. The aircraft was flyable, barely. The asymmetric drag from the damaged wing required constant right rudder pressure to maintain heading. The asymmetric lift required constant left aileron. Lawley's arms were already tired from hours of formation flying. Now he had to maintain these cross-control inputs for another 3 hours to reach England. The co-pilot, Second Lieutenant Harry Mason, took over periodically to give Lawley's muscles relief. They experimented with control positions, discovering that the aircraft had strange handling characteristics. In some configurations, it seemed almost stable. In others, it wanted to roll right and enter a spiral. The bomb load complicated matters. Cabin in the Sky still carried 4,000 pounds of bombs. Standard procedure dictated jettisoning ordnance when damaged, but they were still over occupied territory. Dropping bombs on unknown targets violated orders and potentially endangered civilians. Lawley decided to hold the bombs until they reached the North Sea. This decision meant flying the damaged bomber another 200 miles before reducing weight. The extra weight increased stall speed and reduced controllability. But Lawley had made a command decision based on the situation as he understood it. Cabin in the Sky fell behind the formation. Other crews reported seeing the damaged bomber struggling westward, losing altitude gradually but maintaining basic control. At 15,000 feet, now over the North Sea, Lawley salvoed the bombs. The aircraft immediately became more responsive. The roll tendency lessened slightly, and the control forces decreased. They crossed the English coast at 8,000 feet, still descending. Lawley radioed ahead to their base at Molesworth, declaring an emergency. ground crews prepared for a crash landing. Ambulances and fire trucks positioned themselves along the runway. The approach required careful planning. Lawley couldn't afford a normal traffic pattern because the aircraft's asymmetric handling made turning unpredictable. Instead, he set up a long, straight-in approach from miles out. He configured the aircraft with partial flaps, concerned that full flaps might create too much asymmetric lift. At 500 feet, the bomber was stable but crabbed significantly to the left, compensating for the right roll tendency. Lawley reduced power gradually, allowing the aircraft to settle. At 100 feet, he was committed. At 50 feet, the right wing started to drop. Full left aileron arrested the roll. The main wheels touched simultaneously, a perfect landing under impossible circumstances. Cabin in the sky rolled out, still controllable on the ground despite asymmetric drag trying to pull it right. Lawley used differential braking and rudder to maintain the centerline. When the aircraft finally stopped, ground crews found Lawley's arms trembling from muscle exhaustion. The incident generated significant interest among Army Air Force technical staff. A bomber had survived the loss of a major wing section and successfully landed. Conventional wisdom had said this was impossible. Aerodynamics textbooks explained that losing a wingtip would create unrecoverable asymmetric lift. Yet here was physical evidence that the textbooks were incomplete. Boeing engineers examined the damaged wing carefully. They found that this structural failure had been relatively clean. The wing spar had fractured, but the break occurred at a bulkhead location where structure was reinforced. This might have prevented further failure. The remaining wing section, though damaged, retained enough structural integrity to support flight loads. The aerodynamics were less clear. Theoretically, the aircraft should have been uncontrollable. But theory assumed steady-state flight conditions. Combat flight was anything but steady. The pilot had been making constant control inputs, never allowing the aircraft to settle into a stable trim condition. Perhaps the secret was to keep fighting the aircraft, never letting it establish the death spiral that aerodynamics predicted. The Army Air Force issued a technical bulletin describing the incident, but offered little guidance. Pilots were informed that controlled flight might be possible with major wing damage. But procedures for achieving this control were not specified because engineers did not fully understand what had happened. Other incidents followed. On November 3, 1943, a B-24 from the 389th Bomb Group lost its entire right wingtip to flak over Wilhelmshaven. The pilot, Lieutenant James Stewart, not the famous actor, managed to fly the bomber 400 miles back to England and landed successfully. His technique was similar to Lawley's: crossed controls, constant muscle pressure, and never allowing the aircraft to settle into trim. On December 20, 1943, a B-17 from the 91st Bomb Group lost 8 feet of left wing to a mid-air collision. The pilot, Lieutenant Robert Hughes, not only maintained control but completed the bomb run before returning to England. Hughes reported that he had to maintain full right aileron and significant right rudder throughout the flight. His arms were completely exhausted by the time he landed. These cases established a pattern. Bombers could survive major wing damage if pilots fought the aircraft continuously. But the physical effort was enormous, and success was not guaranteed. Many bombers with similar damage never made it home. The difference between survival and catastrophe seemed to depend on factors that were not yet understood. The Army Air Force's Air Technical Service Command established a special investigation team in early 1944 to study asymmetric wing damage. The team included aerodynamicists from Wright Field, structural engineers from Boeing and Consolidated, and experienced combat pilots. Their mission was to understand how bombers could survive damage that theory said should be fatal. The investigation began with fundamental aerodynamics. Aircraft lift is generated by the pressure differential between upper and lower wing surfaces. As air flows over the curved upper surface, it accelerates, creating lower pressure above the wing than below. This pressure differential, multiplied by wing area, produces lift. For a normal aircraft, lift is symmetrically distributed across both wings. The center of lift aligns with the center of gravity, creating balanced flight. If one wing loses its tip, that wing generates less lift. The asymmetry creates a rolling moment around the aircraft's longitudinal axis. The magnitude of this rolling moment depends on several factors. First, the amount of wing area lost. Losing 10 feet from a 103-foot span removes approximately 10% of one wing's area. Second, the location of the lost area. Wingtips generate proportionally more lift than root sections because they operate in less disturbed airflow. Third, the flight conditions. High angles of attack increase lift coefficients, magnifying the asymmetry. Simple calculations suggested that losing 10 feet of wingtip should create a rolling moment that exceeded the aircraft's available aileron authority. Ailerons work by changing the wing's camber, increasing lift on one side while decreasing it on the other, but ailerons are relatively small surfaces. The B-17's ailerons spanned approximately 20% of the wing area. Creating enough differential lift to counter a 10% wing loss seemed mathematically impossible. Yet pilots were doing it. The investigation team hypothesized that pilots were using techniques beyond simple aileron deflection. They were likely using rudder to create yaw, which induced roll through secondary effects. They might be using asymmetric thrust from the engines. They were certainly using elevator to control pitch, which affected angle of attack and thus the total lift generated. To test these hypotheses, the team needed data from controlled experiments. But deliberately damaging bombers for testing was impractical. Instead, they turned to mathematical modeling and wind tunnel testing. The wind tunnel tests revealed surprising results. When a Model B-17 with a shortened wing was placed in the airstream at various attitudes, the asymmetric rolling moment varied significantly with angle of attack. At low angles of attack, corresponding to high-speed flight, the rolling moment was severe. At higher angles of attack, corresponding to slower flight, the rolling moment decreased. This seemed counterintuitive. Higher angles of attack meant more lift, which should magnify asymmetry. But the wind tunnel showed that the relationship was nonlinear. The damaged wing's stall characteristics changed. Flow separation occurred earlier on the damaged wing, limiting how much additional lift it could generate. Meanwhile, the undamaged wing continued to produce lift efficiently. The net effect was that the asymmetry actually decreased at high angles of attack within certain limits. This suggested a technique. Pilots should fly damaged bombers at higher than normal angles of attack, accepting slower speeds in exchange for more controllable handling. The investigation team also examined control authority. The B-17's aileron system provided approximately 20 degrees of deflection. Typical cruise flight used perhaps 2 to 3 degrees. This left substantial margin. If a pilot used full aileron deflection, the differential lift might be sufficient to counter moderate wing damage. Rudder provided additional capability through cross-control. When a pilot applies rudder, the aircraft yaws. This yaw changes the relative wind direction over the wings, effectively increasing the angle of attack on one wing while decreasing it on the other. The differential lift from this yaw-induced angle of attack change can help counter asymmetric wing damage. The investigation team calculated that a combination of full aileron, significant rudder, and careful angle of attack management could theoretically maintain control with up to 15% wing loss on one side. Beyond that threshold, the mathematical models predicted loss of control. But the models made assumptions about steady flight that combat conditions might violate. Combat pilots were not flying steady. They were constantly adjusting, fighting turbulence, avoiding other aircraft, taking evasive action. In this dynamic environment, the aircraft never settled into the steady-state conditions that mathematical models assumed. Perhaps this constant maneuvering was actually helping maintain control by preventing the aircraft from establishing the unstable trim condition that would lead to loss of control. The structural investigation parallel tracked the aerodynamics work. Boeing engineers examined damaged wings that had been salvaged from crashed or scrapped aircraft. They found that wing structure included significant safety margins. The main spar was designed to handle ultimate loads far exceeding normal flight conditions. When a wingtip was severed, the remaining structure was subjected to unusual bending moments. The asymmetric lift created torsional loads that the wing was not specifically designed to resist. Yet the structure generally held together because the overall strength margins were sufficient to absorb these unusual loads. The investigation identified critical failure points. The wing root, where the wing joined the fuselage, experienced the highest bending moments. If damage extended too far inboard toward the root, structural failure became likely. The engines, mounted partway out along the wing, created local stress concentrations. Damage near engine mounts was particularly dangerous because it combined structural weakening with the risk of engine loss. Wing fuel tanks posed another danger. The B-17 carried fuel in wing tanks located between the fuselage and the inboard engines. These tanks were protected by self-sealing liners that closed small holes when punctured. But major structural damage could rupture tanks entirely, creating both fire hazards and weight imbalances. The investigation team compiled their findings into a technical document distributed to combat units in summer 1944. The document, designated Technical Memorandum No. 44-18, Flight Characteristics of Bombers with Asymmetric Wing Damage, provided the first systematic guidance for pilots facing this emergency. Armed with technical understanding, training commands began incorporating asymmetric wing damage procedures into pilot curricula. The challenge was teaching techniques without actually damaging aircraft. Flight instructors developed simulations that approximated the handling characteristics. The simplest simulation involved asymmetric power. By reducing power on engines on one side while increasing power on the other, instructors could create a rolling tendency that required crossed controls to counter. This didn't perfectly replicate wing damage, but it taught the basic technique of fighting the aircraft with sustained control inputs. More sophisticated simulations used external devices. Some training bases fabricated large wooden panels that could be temporarily attached to one wing, increasing drag and disrupting airflow. These panels, while not truly replicating missing wing structure, created handling challenges that required similar piloting techniques. Ground school instruction explained the aerodynamics. Pilots learned about asymmetric lift, rolling moments, and the relationship between angle of attack and controllability. They learned to recognize the early signs of loss of control, increasing bank angle despite opposite aileron input, sluggish response to controls, and buffeting from disturbed airflow. The training emphasized muscle endurance. Holding cross controls for hours required physical strength that many pilots had not developed. Physical training programs added exercises specifically targeting the muscles used in flying: shoulders, forearms, and core. Pilots learned that they could take turns with their co-pilots, alternating control to prevent muscle exhaustion. Flight simulators, primitive by modern standards but revolutionary for their time, were modified to incorporate asymmetric flight characteristics. Link trainers, the enclosed simulation devices used for instrument training, were programmed to create rolling tendencies that required constant correction. While the visual environment remained unrealistic, the control field taught pilots the required muscle memory. Combat crews arriving at replacement training units in late 1944 received explicit instruction on asymmetric flight procedures. The curriculum included ground school lectures, simulator sessions, and actual flight training with simulated asymmetry. By the time crews deployed to combat theaters, they had at least theoretical knowledge of what to do if they lost part of a wing. The training produced documented improvements in survival rates. Statistical analysis of combat loss reports showed that aircraft with major wing damage were surviving more frequently in late 1944 than in early 1943. Some of this improvement might have resulted from declining German fighter effectiveness, but training contributions were evident in pilot reports describing successful recoveries using taught techniques. First Lieutenant Robert Heinz, who survived the loss of his B-17's left wingtip during a mission to Berlin in March 1945, specifically credited training. "We knew what to do because they taught us. Cross controls, high angle of attack, and fight it all the way home. Without that training, I would have ordered everyone to bail out." The training program's success created a feedback loop. As more pilots survived asymmetric damage, they returned to training units as instructors, bringing combat experience to the classroom. These experienced pilots refined the techniques, identifying subtle points that textbooks had missed. Captain James McGuire, who survived wing damage twice during his combat tour, became an instructor at transition training in late 1945. McGuire emphasized that asymmetric flight was not about achieving stable trim. "You're never going to trim it out," he told students. "The aircraft is damaged. It doesn't want to fly straight. Your job is to force it to fly straight anyway for as long as necessary to get home." McGuire taught specific power management techniques. He explained that engine power on the damaged side should be reduced to minimize the torque that exacerbated roll tendencies. Power on the undamaged side should be carefully managed to maintain airspeed without creating excessive asymmetric thrust. The two inboard engines could be synchronized to provide balanced thrust along the centerline. He also taught altitude management. "Don't try to maintain formation altitude, McGuire instructed. Let the aircraft descend gradually to denser air where it will be more controllable. But don't descend so fast that you overstress the damaged structure. Accept 500 feet per minute descent as normal and plan your route accordingly. These practical details, learned through hard experience, made training progressively more effective. By war's end, the Army Air Forces had developed a systematic approach to an emergency that had seemed unsurvivable just 2 years earlier. February 1, 1943, Tunis, Tunisia. The mission had been a disaster from the start. B-17F All-American, piloted by Lieutenant Kendrick Bragg, had been struck by a Messerschmitt Bf-109 in a way that defied belief. The German fighter had collided with the bomber, but rather than destroying both aircraft, the fighter had sliced through the B-17's fuselage just aft of the radio compartment. The impact nearly severed the bomber in two. The fuselage remained connected only by the lower longerons and the control cables running through the floor. The entire tail section, including the vertical and horizontal stabilizers, hung by these slender threads of aluminum and steel cable. Through the gaping wound in the fuselage, crew members could see daylight and, terrifyingly, the ground 20,000 feet below. Bragg felt the impact but didn't immediately understand what had happened. The control yoke lurched in his hands, then went mushy. He tried to move the elevator, and the aircraft responded sluggishly. The rudder seemed functional but required excessive force. The aircraft was still flying, but something was catastrophically wrong. The navigator, Second Lieutenant Harry Newsel, left his position and worked his way aft to assess damage. What he discovered seemed impossible. The fuselage had a gap almost 4 feet wide. The structural members that gave the fuselage its tubular strength were simply gone, cut cleanly by the fighter's wing and propeller. The tail section was hanging from the fuselage only by luck and the strength of a few cables. Newsel returned to the cockpit and described what he'd seen. Bragg's first instinct was to order bail out. An aircraft this damaged could not possibly reach base. But when he looked at his instruments, he saw that airspeed and altitude were stable. The aircraft was flying somehow. If it was flying now, perhaps it could continue flying long enough to reach friendly territory. The decision to attempt a landing rather than bailing out over enemy or occupied territory was not made lightly. Bragg consulted with his co-pilot, Lieutenant Alan Ramin. They discussed their options. Bailing out meant certain capture or worse. Some crew members would likely be injured during bailout. The aircraft, while severely damaged, seemed marginally controllable. They decided to try for home. The flight back to base required 2 hours of sustained concentration. Bragg discovered that he could maintain straight and level flight by using unusually large control inputs and accepting sluggish response. The elevator required forces far exceeding normal, suggesting that the control cables were binding or had lost mechanical advantage due to the structural damage. Turns were particularly challenging. Banking right required careful coordination of aileron and rudder, and the aircraft wanted to continue rolling once a turn started. Bragg had to lead his recovery, starting the rollout before reaching his desired heading because the response was so delayed. The damage created unusual aerodynamic effects. The gap in the fuselage disrupted airflow over the tail section, reducing its effectiveness. The dangling tail created drag that required constant power to overcome. Fuel consumption increased significantly, and Bragg worried whether they had enough fuel to reach base. Every few minutes, Newsel went aft to check the structural connection. Each time he reported that the tail was still attached, though the gap seemed to be widening slightly. The aluminum skin was tearing gradually and the control cables showed signs of fraying. The structural situation was deteriorating, but slowly enough that they might make it. At 30 miles from base, Bragg began his descent. He reduced power gradually, concerned that rapid changes might overstress the structure. The aircraft descended at 500 feet per minute, a rate that felt stable. At 5,000 feet, base tower cleared them for straight-in approach. Emergency crews were standing by. The approach required extreme concentration. Bragg configured the aircraft with partial flaps, worried that full flaps might create loads the damaged structure couldn't handle. He maintained slightly higher than normal airspeed to ensure adequate control authority. At 500 feet, committed to landing, he started reducing power. The touchdown was firm but controlled. The instant the wheels contacted the runway, Bragg worried the impact might break the tail off entirely. But the structure held. He maintained directional control with rudder and differential braking, allowing the aircraft to decelerate gradually. When All American finally stopped, ground crews approached cautiously, uncertain whether the tail might separate at any moment. Maintenance officers examining the aircraft afterwards declared it a constructive total loss. The structural damage was too extensive for practical repair, but the aircraft had flown 200 miles and landed with all crew members safe. Photographs of the damaged bomber, showing the massive fuselage gap, became iconic images of B-17 structural resilience. The survival of B-17 Lucky Lady on April 29, 1944, demonstrated both the structural strength of Boeing's design and the skill required to fly severely damaged aircraft. The bomber, assigned to the 388th Bomb Group, took multiple flak hits during a mission to Berlin that destroyed nearly 12 feet of its left wing. First Lieutenant John McCrary, Lucky Lady's pilot, experienced the damage as a violent explosion followed by immediate roll to the left. The aircraft inverted within seconds. McCrary instinctively pushed forward on the yoke and applied full right aileron, not understanding yet what had happened but recognizing that the aircraft was out of control. The bomber completed a full 360-degree roll before McCrary regained some semblance of control. At that point, he could see the damaged wing through his side window. The wingtip was simply gone, with jagged aluminum and exposed internal structure showing where it had been. The aircraft did not want to fly straight. Every moment required active pilot input. McCrary called for his co-pilot, Second Lieutenant Thomas Riley, to help on the controls. With both pilots pulling and pushing, they managed to arrest the roll and establish something approximating straight flight, though the aircraft maintained a constant 20-degree left bank. Lucky Lady fell out of formation immediately. The other bombers continued toward the target, while McCrary fought to control his damaged aircraft. He considered ordering bailout, but the aircraft was flying, even if barely. He decided to see if he could coax it home. The flight from Berlin to England covered over 600 miles. McCrary and Riley traded off on the controls every 15 minutes. Each man's arms burning from the constant muscle pressure required to maintain control. They experimented with power settings, discovering that reducing power on both left side engines helped reduce the roll tendency, even though it cost them airspeed. They also adjusted trim continuously, though trim alone could not compensate for the severe asymmetry. McCrary described the experience. It was like arm wrestling with the airplane for 3 hours. You couldn't relax for a second. The moment you eased off the pressure, the wing would drop and the roll would start. At 150 miles from their base at Nettishall, McCrary radioed ahead declaring an emergency. The tower controller asked if he could maintain altitude. McCrary replied that he was descending slowly and couldn't stop it. He estimated he'd cross the coast at 8,000 feet and reach base at around 3,000 feet. The controller cleared him for immediate landing upon arrival. The approach challenged everything McCrary had learned about flying. Normal landing procedures assumed symmetric aircraft handling. Lucky Lady required an approach angled to compensate for its natural left bank. McCrary set up a long final approach from 5 miles out, giving himself maximum time to make small corrections. The landing gear extended normally, one of the few systems still functioning properly. Flaps were more problematic. McCrary extended them incrementally, checking handling after each notch of flaps. Full flaps created too much roll tendency, so he landed with only half flaps extended. The final approach required constant attention. The aircraft wanted to roll left, requiring right aileron. The asymmetric drag wanted to yaw the aircraft, requiring right rudder. The damaged structure created unusual buffeting that made it difficult to judge airspeed accurately. At 100 feet, McCrary reduced power on the remaining engines smoothly. The aircraft settled toward the runway, still banked left. At the last moment, McCrary added a burst of power on the right engines to level the wings. The wheels touched nearly simultaneously, and Lucky Lady was down. Ground crews later measured the structural damage and calculated that the aircraft had lost approximately 22% of one wing's area. According to contemporary aerodynamic theory, this should have made controlled flight impossible. Yet McCrary and Riley had flown the aircraft for over 3 hours and landed successfully. Lucky Lady was repaired and returned to service, one of the relatively few bombers with such extensive damage that could be economically rebuilt. The aircraft completed its combat tour and survived the war, a testament both to Boeing's engineering and to the crew's skill. While B-17s dominated the publicity around asymmetric wing damage survival, B-24 Liberators faced similar challenges with somewhat different outcomes. The B-24's high aspect ratio Davis wing, while aerodynamically efficient, proved less forgiving when damaged. On March 18, 1944, AB-24J from the 453rd Bomb Group lost approximately 8 feet of right wing to flak over Friedrichshafen. First Lieutenant Samuel Barron, the pilot, immediately recognized the aircraft was in trouble. The roll tendency was even more severe than similar damage would create on a B-17, likely due to the B-24's thinner wing section and different lift distribution. Barron fought the controls with his co-pilot, Second Lieutenant Robert Hayes. They discovered that the B-24 required essentially full aileron deflection to prevent roll, leaving no margin for maneuvering. Any attempt to turn right was impossible. Left turns required careful power management to avoid over-rotating. The aircraft's flight manual provided no guidance for this situation. Barron relied on instinct and basic aerodynamic knowledge. He knew that speed gave him control authority, so he maintained higher than normal airspeed by accepting a gradual descent. He knew that altitude gave him time to recover from upsets, so he descended slowly rather than trying to maintain level flight. The B-24's tricycle landing gear created additional challenges. The nose wheel steering system required hydraulic pressure that might be compromised. Barron checked his hydraulic gauges and found pressure was low but still present. He worried whether the gear would extend properly or whether he'd face a belly landing in addition to the wing damage. At 50 miles from base, Barron attempted to extend the landing gear. The nose gear extended and showed locked. The right main gear extended and locked. The left main gear extended, but did not lock. Barron recycled the gear, retracting and extending again. On the second attempt, all 3 legs showed locked.